Metamorphic rocks are rocks that have been altered or metamorphosed from one type of rock into another. For example, let's start with this sedimentary rock called a shale. Shales are a type of mudstone composed of very fine clay minerals or silt-sized particles. Under the right conditions, some shales contain a lot of organic material and contain fossils, such as this sample containing ferns that have been well preserved through a process called carbonization. The shale is our parent rock, also known as the protolith, that exists before any metamorphism occurs. Now let's subject the shale to some metamorphic conditions, which will certainly include some heat, along with some hot, solution-rich hydrothermal fluids percolating through fractures and pore spaces, facilitating chemical reactions. Add in some intense pressure that puts those rocks in a squeeze, and you're going to alter that rock even further. When it's all finished, our shale has been completely altered into a new rock, in this case, one that we would classify as a schist. There are two basic types of metamorphism. One is contact metamorphism, which only involves heat and perhaps hydrothermal fluids, such as a result of magma or lava that comes into contact or is in close proximity to pre-existing rock, either as an igneous intrusion, a volcanic eruption, or possibly both. This type of metamorphism may also be more localized, occurring only in the vicinity of the igneous activity. Regional or mountain belt metamorphism also involves heat and hydrothermal fluids, but also intense pressure associated with mountain building processes along convergent plate boundaries. This type of metamorphism occurs over large geographic distances at scales large enough to form Himalayan-sized mountain ranges and/or volcanic arcs. The types of metamorphic rocks that form will vary depending on the temperature and pressure conditions placed on the protolith. Low-grade metamorphic rocks form under relatively low temperature and/or pressure regimes, whereas high-grade metamorphic rocks form under high temperatures and/or pressures, with intermediate-grade metamorphic rocks forming somewhere in between. Under high-grade metamorphic conditions, partial melting of the felsic minerals may occur, producing felsic or granitic magmas. If the conditions continue to increase, any remaining mafic minerals will melt, recycling everything into magma, meaning we'll basically transition fully out of the metamorphic stage and back into the igneous stage of the rock cycle. One of the ways that we can interpret the metamorphic grade of a metamorphic rock is based on the mineralogy. There are several known minerals that commonly appear in metamorphic rocks under different temperature and pressure conditions. In low to intermediate grade metamorphic rocks, the clay minerals, such as those found in our shale protolith, get agitated and begin to recrystallize as mica minerals, such as chlorite, a green-colored mica, the light-colored muscovite mica, or the dark-colored biotite mica, all depending on the mineral chemistry of the protolith. Once things move into the intermediate grade, garnet, a common metamorphic mineral and signature of many metamorphic rocks, will begin to crystallize. Depending on the chemistry of the rock, other minerals such as staurolite or kyanite may form, and at high grades the mineral sillimanite may appear. The presence of one or more of these minerals in metamorphic rocks gives geologists insight into the probable temperature and pressure conditions that the rock experienced. For rocks that have experienced regional metamorphism, a distinctive texture known as foliation will develop that will be informative as to what grade of metamorphism occurred, high, low, or something in between. Foliation is basically a metamorphic layering that develops as a result of differential pressure, meaning the pressure is not distributed equally on the rock in all directions, but has a higher pressure from one or more direction than in others. The metamorphic rock on the left has been foliated, producing a series of alternating light and dark layers, or bands, that the rock on the right is lacking. Therefore, we know that the rock on the left experienced regional metamorphism, whereas the rock on the right contact metamorphism only. So, how does this differential pressure produce this metamorphic layering we call foliation? Imagine that we start off with a granite protolith. This igneous rock, which cooled slowly beneath the surface, solidified into an aggregate of mostly felsic minerals that crystallized and are oriented in random positions. If we later subject that granite to some regional metamorphism, the heat, in combination with the differential pressure, is going to rotate and reorient those mineral crystals into parallel layers that are perpendicular to the direction of the pressure. In addition, when it gets hot enough, the felsic minerals will get agitated as they approach their melting temperature and begin to separate away from the mafic minerals, producing the light and dark banding seen here. When it's over, our granite protolith has been metamorphosed into a new high-grade metamorphic rock that we call a gneiss. Let's run through the sequence of foliated metamorphic rocks that would form if our shale protolith, the one with those lovely fern fossils, progresses through low-grade regional metamorphism all the way through to high-grade metamorphism. Shale tends to break or split along the plane of the original horizontal layers that are composed primarily of fine clay. As that shale, though, begins to experience low-grade metamorphic conditions, the pressure will begin to rotate and realign all those fine layered clay particles into a new orientation perpendicular to the direction of the pressure. This produces a new set of nearly parallel metamorphic layers or foliation that in most instances will be in a completely different orientation than the original horizontal sedimentary layers. In addition to the pressure, the heat will also begin to agitate those tiny clay minerals and begin to recrystallize them into very fine mica minerals that are way too small to see with the naked eye, but will harden up the rock and may give it a slight luster or sheen that the original dull shale lacked. Our shale has now been metamorphosed into a slate. Unfortunately, the realignment of the clay minerals and their recrystallization into micas will tend to obliterate any delicate fossils that may have been preserved in the original shale, so those lovely fern impressions will be gone. Regional metamorphism tends to destroy any fossils that may have been preserved in the protolith. The plane of weakness in the rock has also been altered, so where the shale protolith would have preferentially split along the plane of the original sedimentary layers, the slate now prefers to split along the plane of the foliated layers. This is called slaty cleavage. If temperatures and pressures continue to rise, we will transition into a new low to intermediate grade metamorphic rock. At this stage, our mica minerals are still too small to see with the naked eye, but they will have continued to crystallize and have grown big enough to give the rock a shiny, reflective luster that may even appear metallic. Subtle changes in the direction or amount of pressure may deform the foliated layers that were nearly parallel in the slate, giving them a wrinkled or crenulated appearance. Our slate is no longer a slate, but has now been further metamorphosed into a new type of rock we classify as a phyllite. But let's keep going and crank the temperature and pressure a little higher and move completely into intermediate grade metamorphism, where a new rock called a schist emerges. By now, all those mica crystals have grown large enough that they can be seen with the naked eye, appearing as small to large flakes that give the rock a kind of scaly appearance. The reflective surfaces of the micas also give the rock a shiny luster like the phyllite, which may appear metallic, and the well-defined foliated layers have been replaced with coarsely aligned layers of mica. This is defined as a schistose texture, and at this point is looking very different than our shale protolith. Variations in schistose textures will depend on the type or types of mica, as well as any other metamorphic minerals that form. When we identify a metamorphic rock with a schistose texture, rather than simply calling it a schist, we will prefix the name with the dominant mineralogy that is present. For the micas, muscovite is probably the most common, but biotite and chlorite are others, giving us muscovite schist, biotite schist, or chlorite schist. In addition to the mica minerals, other minerals may begin to form, the most common and prevalent being garnet, but there are others such as kyanite and staurolite that may also appear at slightly higher intermediate temperatures and pressures. Either way, when any of these minerals are also present, we will amend the name and call the rock a muscovite garnet schist or biotite garnet schist, for example. Finally, let's transition even further into high-grade metamorphic conditions and see what happens. Temperatures are hot and the pressures are extreme. The schistose texture is now replaced as recrystallization and alteration of the minerals present in the rock becomes more granular and begins to segregate into coarse crystalline bands of felsic and mafic minerals. This new rock is called a gneiss. The G is silent and is characterized by the foliated light and dark bands of minerals that we call gneissic banding. Gneiss is a product of intense regional metamorphism that forms deep in the earth at the roots of a mountain range. We find gneisses and garnet schists locally in our area along the Potomac River at Great Falls and in Rock Creek Park in Washington, D.C., which tells us that sometime in the geologic past there used to be a Himalayan-sized mountain range right here in our nation's capital. At this point, if metamorphic conditions increase even further, the rock will basically begin to melt, returning us to the igneous stage of the rock cycle. So here's the overall sequence of rocks that will form under increasing regional metamorphic conditions. As a general rule, slates, phylites, and schists have some type of shale or mudstone protolith, which under high-grade metamorphic conditions may eventually produce a gneiss. However, when we identify a gneiss, this type of metamorphic rock often has an igneous or sedimentary protolith, such as a granite or a variety of sandstone. We would need additional information or evidence from the field where the rock was located to better interpret the likely protolith. For rocks that experience contact metamorphism only, there is no pressure, so there is no foliation. Heat, along with some hydrothermal fluids, is going to be the only agent of metamorphism acting on the rocks. One way to think about this process is if you have some soft clay that you're using to mold into pottery. You take those molds and stick them into a furnace and heat them up. And when you're finished, the clay has been baked by the heat and hardened into sturdy clay pottery. A similar process plays out when an intrusion of magma or a flow of lava comes into contact with the cold, pre-existing rock it is cutting through or flowing over. The heat from that molten material radiates out and alters the surrounding rocks. One common non-foliated metamorphic rock that you have certainly heard of is marble. Marble begins as a type of sedimentary rock called a limestone. This protolith is composed primarily of calcium carbonate in the form of chemical deposits of the mineral calcite, preserved shell material, or both. In the presence of heat and hydrothermal fluids, the calcium carbonate material will begin to recrystallize and become more granular as conditions increase from low to high-grade temperatures. The movement of hydrothermal fluids may mobilize and precipitate out dark swirls of oxide and sulfide minerals such as hematite, pyrite, and galena, and because the rock is not experiencing differential pressure, original sedimentary layers or laminations may be preserved as well. One of the keys to identifying a marble is that it reacts with a little bit of hydrochloric acid. Recall that the mineral calcite, which is calcium carbonate, reacts with acid. So when we have a rock that is composed primarily of calcium carbonate, it too will react. The acid test can come in handy in helping distinguish marble from another metamorphic rock that may, at first glance, appear similar. Quartzite is a non-foliated metamorphic rock that had a quartz-rich sandstone protolith. As with the marble, the intense heat and percolation of hydrothermal fluids through the rock will begin to alter the individual quartz sand grains, recrystallizing and fusing them together, giving the rock a crystalline, sometimes sugary texture. If there are any visible sedimentary layers in the sandstone, they may be preserved as well. For our purposes, a quick and easy way to distinguish between a quartzite and a marble is to test the rock with acid and see if it reacts. If it doesn't effervesce, you probably have a quartzite. Also, recall that quartz is a 7 on the Mohs hardness scale, so it's a hard and chemically stable mineral. So a rock that is composed of fused quartz grains is going to be hard as well.